NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve floor bracket equations using the structured algorithm for what we call special case 2. The general form we will study is floor of x plus floor of ax plus floor of bx plus floor of cx equals k, where a, b, c, and k are integers. Our goal is to express x as an integer part plus a fractional part, simplify the equation, and derive a clean formula for the integer part. Step 1. Write x as n plus p, where n is the integer part and p is the fractional part with p between 0 inclusive and 1 exclusive. Visually, p lives on the unit interval from 0 to 1. Step 2. Expand each multiple of x. Ax equals an plus ap, bx equals bn plus bp, cx equals cn plus cp. Because p is between 0 and 1, ap ranges from 0 to a, so the floor of ap can be any integer from 0 up to a minus 1. The same goes for bp and cp. Step 3. Substitute x equals n plus p into the original equation. Since n, an, bn, and cn are integers, they pass straight through the floor. Also, the floor of p equals 0, because p is in the interval from 0 to 1. Group the n terms together. Step 4. Solve for the integer part, n. Define S as the sum of the three floor pieces, floor AP plus floor BP plus floor CP. From the ranges, S can be as small as 0 and as large as a plus B plus C minus 3. Step 5. For n to be an integer, the denominator 1 plus a plus B plus C must divide the numerator. That is, 1 plus a plus B plus C divides k minus S for some S in the valid range. After you find a valid n, you then determine which p values make the chosen S equal to floor AP plus floor BP plus floor CP. Let's see a clean example to make this concrete. Suppose floor of x plus floor of 2x plus floor of 3x plus floor of 4x equals 20. Using x equals n plus p, the integer parts give 10n because 1 plus 2 plus 3 plus 4 equals 10. The fractional floors contribute S equals floor of 2p plus floor of 3p plus floor of 4p, which can range from 0 to 6. So 10n equals 20 minus s. We need 20 minus s to be a multiple of 10. The simplest choice is s equals 0, which gives n equals 2. S equals 0 means floor 2p, floor 3p, and floor 4p are all 0. That forces p to be less than 1/4. Therefore, x ranges from 2 up to 2.25. Here is a quick visual of the solution interval for x in our example. To summarize, write x as n plus p with p in the unit interval. Expand ax, bx, and cx, and use floors to separate integer parts from fractional parts. The equation becomes n times 1 plus a plus b plus c plus s equals k, where s is the sum of the fractional floors. Solve for n as a fraction. Enforce the divisibility condition, and finally locate p by matching s. The key formula to remember is n equals k minus s over 1 plus a plus b plus c, with s between 0 and a plus b plus c minus 3 chosen to satisfy the divisibility. In this lesson, we will solve the floor equation. Left bracket x right bracket plus left bracket 2x right bracket plus left bracket 4x right bracket equals 15. We'll follow a clear algorithm using the integer and fractional parts of x. Here is the problem statement. We will work step by step, keeping the narration perfectly aligned with the visuals on screen. Step 1. Identify the constants from the equation. We read the coefficients and the target sum. So a equals 2, b equals 4, and k equals 15. Step 2. Write x as n plus p, where n is the integer part, and p is the fractional part with 0 less than or equal to p and p less than 1. Then use the algorithm formula for n. N equals k minus the sum of floor of AP and floor of BP, all divided by a plus b plus 1. Step 3. We need n to be an integer. The denominator is 7, so the numerator must be divisible by 7. That means 15 minus the sum must be a multiple of 7. Testing sum 0 through 4. The value 1 works because 15 minus 1 equals 14, and 14 over 7 equals 2. So n equals 2, and the sum of floor of 2p and floor of 4p equals 1. Step 4. We analyze the condition floor of 2p plus floor of 4p equals 1 by working on a number line for p between 0 and 1. We will visualize the intervals that make each floor value equal to 0 or 1. Case A. If floor of 2p equals 0, then 0 less than or equal to p is less than 1/2. If floor of 4p equals 1, then p is between 1/4 and 1/2. Their intersection is p in the interval from 1/4 inclusive to 1/2 exclusive. We highlight these intervals and their overlap. Case B. If floor of 2p equals 1, then p is between 1/2 and 1. And if floor of 4p equals 0, then p is between 0 and 1/4. These two intervals do not overlap, so the intersection is empty. Step 5. We now combine n equals 2 with p in the interval 1/4 to 1/2. That gives x equals n plus p between 2 plus 1/4 and 2 plus 1/2, with the right endpoint excluded. So the solution set is the interval left bracket 9/4, 5, halves right parenthesis. Quick verification. Choose a value inside the interval, for example x equals 2.3. Then floor of x equals 2, floor of 2x equals 4, and floor of 4x equals 9. The sum is 15, matching the equation. Final result. The complete solution set is the interval left bracket 9/4, 5, halves right parenthesis. In this lesson, we will solve the equation floor of x plus floor of 2x plus floor of 4x equals 13. Throughout this example, square brackets indicate the floor function. We will follow a structured algorithm, identify constants, decompose x into integer and fractional parts, analyze possible values, and test for integer solutions. Step 1. Identify the constants. Here a equals 2, b equals 4, and k equals 13. Step 2. Decompose x into its integer and fractional parts. Write x equals n plus p, where n is floor of x, and p is in the interval from 0, inclusive, to 1, exclusive, for the equation floor of x plus floor of 2x plus floor of 4x equals k. This algorithm gives the integer part n as n equals k minus floor of ap plus floor of bp, all over a plus b plus 1. Substituting a equals 2, b equals 4, and k equals 13, we get n equals 13 minus the quantity floor of 2p plus floor of 4p, all over 7. Step 3. Analyze the possible values of floor of 2p and floor of 4p, as p runs from 0 to 1. We split the interval for p at 1/4, 1/2, and 3/4. If p is between 0 and 1/4, both floors are 0, so the sum is 0. If p is between 1/4 and 1/2, floor of 2p is 0 and floor of 4p is 1, sum equals 1. If p is between 1/2 and 3/4, floor of 2p is 1 and floor of 4p is 2, sum equals 3. If p is between 3/4 and 1, floor of 2p is 1 and floor of 4p is 3, sum equals 4. Step 4. Test each possible sum in the formula for n. If the sum is 0, n equals 13 over 7, not an integer. If the sum is 1, n equals 12 over 7, not an integer. If the sum is 3, n equals 10 over 7, not an integer. If the sum is 4, n equals 9 over 7, not an integer. No value of p makes n an integer, therefore the equation has no solution. In this lesson, we will solve the floor function equation, open bracket x plus open bracket 2x plus open bracket 3x close bracket equals 24. In this problem, the square brackets denote the floor function, which returns the greatest integer less than or equal to its input. Step 1. We use the key property of the floor function. The floor of x plus I equals the floor of x plus I, whenever I is an integer. Here, the inner expression open bracket 2x plus open bracket 3x close bracket is itself an integer, so we can simplify. That gives the floor of x plus that integer equals the floor of x plus that integer. Therefore, the left side becomes floor of x plus floor of 2x plus floor of 3x. Step 2. Write x as n plus p, where n is an integer and p is the fractional part, with 0 less than or equal to p and less than 1. Using this, the floor of x is n. The floor of 2x is 2n plus the floor of 2p. The floor of 3x is 3n plus the floor of 3p. Substituting into our equation, we get 6n plus floor of 2p plus floor of 3p equals 24. Step 3. Solve for n. We have n equals 24 minus the sum of floor of 2p and floor of 3p, all divided by 6. Since n must be an integer, the numerator must be a multiple of 6. Also, because p is between 0 and 1, the floor of 2p can only be 0 or 1, and the floor of 3p can be 0, 1, or 2. So their sum is between 0 and 3. Step 4. Since 24 is divisible by 6, the quantity floor of 2p plus floor of 3p must itself be congruent to 0 modulo 6. But it can only take the values 0 through 3. The only option that makes the numerator a multiple of 6 is 0. Therefore, floor of 2p plus floor of 3p equals 0, which forces floor of 2p equals 0 and floor of 3p equals 0. Then n equals 24 divided by 6, which is 4. Step 5. From the condition that floor of 3p equals 0, we get 0 is less than or equal to 3p and less than 1. So 0 is less than or equal to p and less than 1/3. This automatically gives floor of 2p equals 0 as well, because 2p is less than 2/3. So p lies in the interval from 0 inclusive to 1/3 exclusive. Let us visualize that on a number line for p between 0 and 1. Step 6. Combine n equals 4 with 0 less than or equal to p and less than 1/3. That gives x equals n plus p between 4 and 4 plus 1/3. Therefore, the complete solution set is the interval from 4 inclusive to 13/3 exclusive. Final answer x lies in the interval from 4 to 13/3, not including 13/3. In this lesson, we will solve a nested floor function equation step by step, focusing on a clean, visual strategy. Here is the problem. The floor of x plus the floor of 2x plus the floor of 3x inside another floor equals 25. Throughout, square brackets denote the floor function. Step 1. Use the key property. The floor of x plus n equals the floor of x plus n when n is an integer. Because the inner expressions in brackets are integers, we can pull them out of the floor in stages. First, let y be the floor of 2x plus the floor of 3x, which is an integer. Then the floor of x plus y equals the floor of x plus y. Next, apply the same idea inside y. The floor of 2x plus the integer floor of 3x equals the floor of 2x plus the floor of 3x. Therefore, our equation simplifies to floor of x plus floor of 2x plus floor of 3x equals 25. Step 2. Split x into its integer and fractional parts. Let x equal n plus p, where n is the floor of x and p is in the interval from 0 inclusive to 1 exclusive. Then the floor of 2x equals 2n plus the floor of 2p, and the floor of 3x equals 3n plus the floor of 3p. Substitute into our simplified equation to get 6n plus floor of 2p plus floor of 3p equals 25. Therefore, n equals 25 minus the sum of those two floors, all over 6. Step 3. Determine which values the sum floor of 2p plus floor of 3p can take when p is between 0 and 1. Since 2p is in the interval from 0 to 2, its floor is 0 or 1, and 3p is in 0 to 3, so its floor is 0, 1, or 2. Therefore, the sum can be 0, 1, 2, or 3. For n to be an integer, 25 minus that sum must be divisible by 6. Only when the sum equals 1 does this happen, giving n equals 4. Step 4. Now, we must find all p in the interval from 0 to 1, such that the sum floor of 2p plus floor of 3p equals 1. We will use a number line for p from 0 to 1, marking key points at 1/3, 1/2, and 2/3. The condition floor of 2p equals 0 means p is less than 1/2. The condition floor of 3p equals 1 means p is between 1/3 and 2/3. Their intersection is p from 1/3 inclusive to 1/2 exclusive. Step 5. Convert the p range into an x range using x equals n plus p and n equals 4. So 4 plus 1/3 is less than or equal to x, which is less than 4 plus 1/2. In improper fractions, this is 13/3 less than or equal to x, which is less than 9/2. Therefore, the solution set is the interval from 13/3 inclusive to 9/2 exclusive. In this lesson, we will solve a nested floor function equation step by step, focusing on an intuitive visual approach. Here is our problem. The floor of x plus the floor of 2x plus the floor of 3x inside the floor equals 20. We will simplify, split x into its integer and fractional parts, narrow the possible cases, and then find the full solution set for x. Step 1. Use the key property. The floor of x plus k equals the floor of x plus k whenever k is an integer. Because the floor of 2x plus the floor of 3x is an integer, we can pull it out of the outer floor. So the equation becomes the floor of x plus the floor of 2x plus the floor of 3x equals 20. Step 2. Split x into its integer and fractional parts. Let x equal n plus p, where n is the floor of x and p is the fractional part with p between 0 and 1. Substitute into our equation and simplify carefully. The floor of 2 times n plus p becomes 2n plus the floor of 2p, and the floor of 3 times n plus p becomes 3n plus the floor of 3p. Altogether, this gives 6n plus the floor of 2p plus the floor of 3p equals 20. Solving for n, we get n equals 20 minus the sum of those floors, all divided by 6. Step 3. Now analyze the possible values of the sum s, defined as the floor of 2p plus the floor of 3p. Since p is between 0 and 1, the floor of 2p can be 0 or 1, and the floor of 3p can be 0, 1, or 2. So s can be 0, 1, 2, or 3. For n to be an integer, 20 minus s must be divisible by 6. Let us list s and the corresponding value of n. Only when s equals 2 does n come out as exactly 3. Step 4. We now solve for p when the sum s equals 2. The valid combination is the floor of 2p equals 1 and the floor of 3p equals 1. These inequalities give 1/2 less than or equal to p less than 1 and 1/3 less than or equal to p less than 2/3. Their intersection is p in the interval from 1/2 inclusive to 2/3 exclusive. We will visualize this on a number line from 0 to 1. Step 5. We found n equals 3, and p is between 1/2 and 2/3. Therefore, x equals n plus p lies between 3 plus 1/2 and 3 plus 2/3. That is x in the interval from 7/2 to 11/3. In this lesson, we will solve a floor function equation step by step and build strong intuition with visuals. Here is our problem. The floor of x squared plus the floor of 2x squared, all inside a floor, equals 13. Our first goal is to simplify it using a key property of the floor function. Key property. If k is any integer, the floor of a plus k is the floor of a plus k. Here, the floor of 2x squared is always an integer. So, the floor of x squared plus that integer equals the floor of x squared plus the floor of 2x squared. To make the structure clearer, define y as x squared with y greater than or equal to 0. Then our equation becomes floor of y plus floor of 2y equals 13. We'll solve for y first, then map back to x. Here's the key graphical insight. Consider a number line for y. Split y into integer bins, from k up to k plus 1. On each bin, compare the first half from k to k.5, and the second half from k.5 to k plus 1. On the first half, 2y runs from 2k up to just below 2k plus 1, so its floor is 2k. On the second half, 2y runs from 2k plus 1 up to just below 2k plus 2, so its floor is 2k plus 1. Therefore, the sum becomes piecewise, 3k on the first half, and 3k plus 1 on the second half. Now set the sum equal to 13. 3k equals 13 is impossible for an integer k. 3k plus 1 equals 13 gives 3k equals 12, so k equals 4. That pins y between 4 and 5. But which half? Since we use the second half formula 3k plus 1, y must lie in the upper half, from 4.5 to 5. Finally, map from y back to x. Let's draw the graph of y equals x squared. We'll draw a horizontal band for y between 4.5 and 5. The intersections with the parabola correspond to two symmetric x intervals, one negative and one positive. Projecting those to the x-axis gives x between minus square root 5 and minus square root 4.5, and x between square root 4.5 and square root 5. Those are all the solutions. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.